Hi, this is Choosing the Right Load Balancer for your serverless applications. I'm Corina Motoy, and for the next 30 minutes, we are going to focus how and when you should use an AWS load balancer in a serverless architecture. Before we start, a couple of housekeeping rules. This is a 300 level session, hence it is assumed that you have the basic understanding on how an AWS load balancer works and what are the advantages of running serverless applications. Also, we are quite time restricted. So where I feel that there are additional information that you might benefit of, along the session I've inserted certain references so you can watch or listen to them in your spare time. The agenda, we're going to keep it quite brief. We're going to have a short reminder about how the AWS Elastic Load Balancer works and the principles of it. Then we're going to discuss how it actually integrates with the serverless components, and then take all this and showcase some of the architectures that we are seeing today with our customers. Before we go any further, in this session, we are also going to cover concepts around the use of containers. So if you're not yet familiar about how networking works when you're running containers with Fargate, please have a look at this blog post and also at this online tech talk, which will give you details about how ECS and AKS run with Fargate. And let's dive into the topic and start with a short reminder about how the AWS Elastic Load Balancer works. The ALB family consists as of this moment of four load balancers, each of them having their own particularities and fit for certain use cases. You have the application load balancer, which works at the layer 7 of the OC stack and is best suited for the load balancing of HTTP, HTTPS traffic. You then have the network load balancer working at the layer 4 of the OC stack, and that one is best suited when you need high performance and low latency, as it works on as it runs on AWS Hyperplane. Our latest addition to the family is the Gateway Load Balancer, which acts like single entry and exit point and load balances the traffic through Geneve protocol to your virtual appliances, preserving the content of the original traffic. Just for completeness, I've included also the classic load balancer, which is our legacy load balancer. If you're using that today, a migration might be in order, as our development focus is going to be mostly on the newer load balancers. Let's discuss also about the principles around the load balancers, because they might be different, but in the end, they are similar on how they work. That means they automatically distribute incoming application traffic towards the target registered to a target group. So at a very high level, the traffic is accepted by the ELB based on the listeners that you have configured, that is the protocol and the port. And then the request in the case of the LB, or the flows in the request in the concept of the network load balancers, are routed towards the end. The ALB support instances at targets, and specifically with the ALB and NLB, you can also have IP addresses and containers spin up with Fargates as targets. If you need Lambda as a target, that is only possible today with the application load balancer. Just to respect previous Elastic Load Balancer session, I've included also a table that summarizes at a very high level the differences between the load balancers. I've chosen those differences which are relevant for today's session in the context of serverless architecture. So besides target types, which we've briefly discussed earlier, it's worth reminding that static IP is possible nowadays only with the network load balancer, while if you're intending to looking into the HTTP header and route traffic based on any field of that header, you might want to look into the application load balancer. Uh, of course, this brief reminder was by no means intended to cover all the differences between the load balancers. So please, if you'd like to learn more about them and get into more details, this session from last year reInvent from 2019, it's a good session that you would find quite great information. Okay, we've discussed about the principle of the elastic load balancer, and let's see how those apply when it comes of integrating the ELB in a serverless environment. As you know, we have quite an extensive serverless catalog, but for this session, we are going to focus only on those services which have the potential of being part of a load balancing structure, such as the targets. And those services, in our case, are the AWS Lambda and AWS Fargate. As you probably know, Lambda allows you to run code without provisioning or managing servers, while AWS Fargate is our serverless compute engine for containers. Those are the targets, but besides that, we are also going to discuss what are the features that make either APIGW or Elastic Load Balancer a good entry point for your serverless applications. For the ones of you who are not aware, the APIGW is our managed services service that makes it possible for developers to create, publish, and secure APIs at scale. Let's go into this topic and start with having Lambda as a target and discuss a little bit about the benefits of use cases of this deployment. First of all, with Lambda as a target, you can now have the load balancer supporting a mix of compute resources as targets. So you can have Lambda, you can have containers, you can have EC2, all of them under the same HTTP front end. But nothing stops you in the end to have everything serverless because the ALB supports that. Also, you can have your ALB fronting multiple Lambda functions. Another handy thing by having Lambda as a target for the ALB is the fact that now you can take one step further and create custom targets, such as serving a static website just by triggering the code which is sitting in S3 with a Lambda function. How it actually works? Well, you create your load balancer and then you create your target groups with the type Lambda. You can choose to send each listener to a different Lambda function, or you can have multiple listeners going to the same Lambda function. The HTTPS requests are passed by the ALB to Lambda function in JSON format according to the routing rules that you have configured. And in that JSON format, the ALB will add 4 additional headers to each of the requests that it receives. As APIGW, also the ALB supports content encoding header, which you can set. But in case you're not doing that, the ALB will look at the type of the request and set the base 64 encoding either to true or false. For the response coming from Lambda to ALB, it's again in a JSON format and includes the base 64 encoding, the status code, and the headers. Those are mandatory. If the response is base 64 encoding, I mean the flag is set to true, the load balancer decodes the response, gets the binary content, and then it sends back to the client in form of the HTTP response. We've discussed about the benefits and the use cases, and in the wrap-up slide, I would like to discuss also some notes which you should be aware of when you're using Lambda as a target for an ALB. The first one is the fact that you can have a single Lambda function per target group. The Lambda function and the ALB have to be in the same account and the same region. Also, as Lambda function is invoked by a request, there is no WebSocket listener running continuously to accept the connection. Hence, WebSockets are not supported for Lambda as a target for ALB. Last thing, which is worth being called out, is the fact that the ALB health checks for Lambda are supported, and they can be enabled either via by console or by the CLI. One thing to bear in mind is the fact that you're going to pay for Lambda health checks the same as per the Lambda invocation, which is handy to know when you're going to enable those health checks. The second target, serverless target that you can have for an elastic load balancer is Fargate. And let's discuss a little bit about Fargate for ECS. As you know, ECS is Amazon Elastic Container Service and allows you to easily run Docker container applications in AWS. Using Fargate, all the operational overhead is passed over to AWS, and it makes it easier to run those kind of applications. And keeping the ALB as that single front end, you can again have a mix of compute, which can be containers, EC2 instances, or Lambda functions, up to you. Having Fargate, which manages all the scaling of the containers, allows you to build microservices applications with spiky, unpredictable traffic patterns, as again, Fargate is going to take care of the scaling part. So let's work for you. Also, it's worth noticing that, being said, that Fargate for ECS is also supported by the Network Load Balancer. So in case you want to load balance TCP UDP based application, then this is a good deployment. Lastly, you can also deploy multiple services using a single listener or a single ALB, which is a great feature when you're dealing with microservices applications. Again, you can have multiple services using a single listener. Quite handy. How it actually works, you have your AWS account and you're deploying a VPC to subnets. Let's have this as an example. You have your application load balancer, and then you specify the target group, which that exactly target group will also be specified in the service definition for ECS. In that service definition, you'll also going to specify the launch type, which is going to be Fargate, and the AWS VPC network mode is required. While establishing that, those tasks are going to span up inside the subnet and the VPC that you select, and they are going to take IP addresses from that specific CIDR block. One other thing which is important, the target type has to be IP and not instance. And the handy part when we're talking about Fargate and ECS as targets for the ELB is the fact that the clusters can be either in private or public subnets, which is good to know. Again, we've talked about the benefits, the use cases, so let's focus about some good to know stuff on Fargate and ECS. First of all, we've already said LB is a great fit for microservices application. And one of the reasons for that is the fact that allows dynamic host port mapping for containers. Another thing is the fact that the service now supports up to 5 target groups with mixed compute. That means a single service can make use of multiple load balancers. So for example, you can have a load balancer for internal traffic and another load balancer for external traffic. Each container of a task can define its own health checks in the task definition. Again, if the version is running 1.1.0 or higher, but it's recommended to have both the ELB and the container health checks configured, as the status of the targets is controlled by the targets group health check. we talk about ECS, but since 2019, Fargate is also supported for AKS. That means you can deploy your pods to a serverless container data plane using Fargate, and which makes it easier to run Kubernetes applications. This way, the AWS is going to manage the life cycle of the pod and spins up the Fargate worker nodes to run the pods for you. Also, Kubernetes applications often need to be exposed to external traffic, and AKS customers for that leverages the ALB to accomplish this task. Since October 2020, what you used to know as the ALB ingress controller is now called the AWS load balancer controller. And let's get into a little bit more details on that. As with the launch of the AWS load balancer controller, you can now have Fargate as a target not only for the ALB but also for the NLB, as it supports IP address targeting mode for AKS as well. Basically, to create a load balancer for your service, you just have to add the type of the load balancer into the annotation specifying it. One thing which is quite important to be aware of, the pods running on Fargate for now are only supported on private subnets with NAT gateway that can access AWS services but not having a direct route to the internet gateway. Other things which are worth calling out is the fact that the AWS load balancer controllers share ALBs with multiple Kubernetes ingress rules. Support for custom resource called target group binding to support pods using an existing target group. And that way, basically, the load balancer sits completely outside of the Kubernetes, but still manages the targets with the Kubernetes service. In terms of capacity, you can have a maximum of 4 vCPUs and 30 gigabytes of memory per pod. But you also have smaller options that you can choose from. If you're not going to choose any of the options, the AWS is going to do that for you by specifying the smallest configuration. And another feature which is now available since we have the AWS load balancer controller is the fact that we now support fully private clusters. There are still so many details to discuss about the load balancer controller. So you can start by having a look at this blog post. Is since October 2020, and this will give you an introduction, more details about it, and will point you out to additional resources if needed. Also, as we've spoken quite a lot on containers, and you might want to know when new features are coming out, please bookmark this page. It's a GitHub link, which will take you to the public roadmap of our container services, containing details about ECS, AKS, and Fargate. Hopefully by now you have quite a clear understanding on how an elastic load balancer works when it comes to serverless targets. So let's switch a little bit the topic and look at the entry point of a serverless application. Quite often, the discussion that I'm seeing is whether to use an API gateway or an elastic load balancer as that front end to your serverless application. So I'm going in the next couple of minutes just to walk through the similarities and differences when using any of those two services. So one point that stands out when you're talking about the API gateway and ALB is basically the routing, how the requests are routed. API Gateway supports path-based routing based on the URL requested by the client, while the ALB, the Application Load Balancer, has a more extensive routing mechanism. For the ALB, the routing rules can be based on any field in the HTTP request header, such as host header, URL path, URL query string, or even a mix between them. So quite more option for yourself to route your requests. In terms of payload, when integrating with a Lambda function, API Gateway supports 6 megabytes, while the ALB supports 1 megabyte. The responses have the same size in payload as well. Natively for the API gateway, you can configure throttling on the requests to your API. Then specifically for the load balancer, if you need a static IP for your HTTP endpoint, then you can have your ALB, your application load balancer, behind a net or load balancer to provide this functionality. Going a little bit further, both services are highly scalable, but the API gateway has a limit of 10,000 requests per second, while the application load balancer scales automatically. It's worth calling out also the integration bit, as the API gateway can route requests to other AWS managed services with public endpoints such as S3 or SQS or even external endpoints, while ALB is best suited when you want to route your traffic towards private resources, most of the time sitting in a virtual private cloud, in a VPC. Also, both services can be protected by AWS WAF, but HTTP APIs are for now supported only by the integration with the application load balancer. So let's take now all the concepts that we discussed, the principle of a load balancer and the integration with the serverless, and look at some patterns that we are seeing with our customers. And the first one that I would like to discuss is the microservices application architecture. As you all know, this is quite complex, difficult to manage, so let's see how an ALB, an application load balancer, can help transitioning to a serverless architecture with minimum management overhead. So we have our application load balancer distributing requests to two microservices, which can be based on EC2 or containers on EC2. I've chosen ECS services on containers here. Introducing serverless microservices can be done just by deploying a new microservice, a new version of your microservice just on serverless. I've chosen Fargate to deploy my ECS containers, and then you have that microservice in another target group for the application load balancer. And now, looking at the blue-green deployment, you can use the ALB weighted target groups and assign weights for each microservices. Through the weights, the ALB will control the traffic to each microservice. For example, to start with, you will have all the traffic going to microservice 2, the old version, and zero traffic going to microservice 2, the newer version, which is based on serverless. Then you can gradually increase the traffic, the weight of the traffic that goes to your newer serverless microservice. And in the end, you can just have all 100% of the traffic destined for microservice 2 going to the newer version running on Fargate. And this way, Fargate takes over all the operational management of running containers. So you have a fully serverless microservice. And the best part of it, that this is done with zero downtime on your side. Of course, this is just having a Fargate for a new version of your microservice, but nothing stops you to add additional target groups with additional serverless microservices, such as in this case, I've just taken Lambda as an additional microservice tree. All you have to do is basically create another target group for your application load balancer. And you can do that besides having targets, serverless targets for your ALB. Another feature which you might find useful when you're working with microservices applications is the ALB fixed response, which is a feature of the ALB. And basically the ALB does not forward the traffic to the targets, but in return, will just send a custom HTTP message or just a code when a request for a path which is restricted is going to come to the ALB. So this is quite handy. And of course, just deploy as many as you want of the microservices. Just don't forget that we have a limit of 100 target groups for the application load balancer. The deployment that we've spoken about is in one region, but the same principles apply to multiple regions, and you can get advantage of the LB integration with services such as Route 53 or AWS Global Accelerator to route the traffic across multi-region serverless deployment. So whatever you know from using the application load balancer in the past with EC2 instances or containers running on EC2 instances, this is the same possible right now with the serverless application. There are also cases where the network load balancer is best suited when we're talking about microservices applications. So we have, as you know, is best suited to route to load balance TCP UDP request. So you have your network load balancer, and then you have microservice deployed behind it. When would you like that? Well, especially when you have applications with non-HTTP, HTTPS API, when you require high throughput and ultra low latency, and also where you require that static IP, where your applications don't support DNS. So basically you need to have a static IP to be able to route the traffic. The challenge here is the fact that NLB routes flows, not requests. So it's not possible for the NLB to have multiple microservices and to be able to route the traffic to each of those microservices accordingly based on the request type, because it routes flows. So for that reason, an idea would be to have multiple NLBs, each of them with their own microservice, their own service, which, let's be serious, is not quite efficient and not a good practice. So in case you really need a network load balancer for your microservices application, and in the case you need that static IP, one workaround is to have an application load balancer that manages that routing for the requests which are coming from the NLB. So basically the ALB will be part of the NLB target group. This is a workaround. We have a blog post which can give you more details about it, but we're also working on improving that. So please have a look at what's new and our latest updates on the ELB space, and see what we're coming up with on this front. One last pattern which I really want to discuss with you, as I think is quite useful, That is, with API Gateway, usually the customers can create internet-facing APIs in front of their ECS and AKS services. And those are sitting in a VPC, most of the time behind an ALB or a network load balancer. So, when you need to expose your private microservices using API Gateway, you want to do that with an application load balancer when you want to have authenticated access to private microservices using HTTP APIs. For that, you take advantage of what is called API Gateway Private Integration, meaning that you can create an endpoint to your VPC by setting up a VPC link between your API Gateway and the application load balancer. Basically, this VPC link allows you to connect your HTTP API routes to private resources in your AWS VPC. Those resources can be containers launched with Fargate. Why not? So perfectly valid serverless targets. One thing to call out here is the fact that all resources have to be owned by the same AWS account. The same deployment, it's also possible with a network load balancer, and this happens when you have non-HTTP APIs. And you again take advantage of the API private integration with the network load balancer. Again, all the resources have to be in the same AWS account. But one thing here that is quite handy when you have your network load balancer being fronted by the API gateway is the fact that you can configure each service as a specific listener on the network load balancer and use a single VPC link to connect the API gateway to the network load balancer. So when you're creating that private integration in the API gateway, you then define each service using the specific port that is assigned for each service in behind the network load balancer. So this is one quite good way to have a microservices application and an API gateway as a front end. As you've chosen to join the session, I think you're quite interested in the networking part and elastic load balancers. So I strongly advise you to have a look at this reInvent session, that is Net 402, Elastic Load Balancing, a year of innovations, for you to be up to date with the newest features on the load balancers. Hopefully you found this session useful, and thank you so much for taking the time to attend it.